Good. Hello, everyone. We are wrapping up the stuff up in Hope Bay these days. So I'm glad you are here for this talk, because it might be the last time I'll give this talk on Hope Bay, here at least. So the work has been a combination really of geochronology and electric resistivity measurements. A combination of data that I wouldn't have thought was possible 10 years ago or something. So, but here we are with this study, so that's pretty good. The stuff that we've been doing is in very close collaboration with Agnico Eagle, and they've been really great helping us out in that remote area of Hope Bay. So this just shows a map of the Slave Craton. Hope Bay is located up here in the northeastern part of the Slave Craton. So most of the Slave Craton, the greenstone belt of the Slave Craton, there's approximately 30 plus or something, 35 different greenstone belts spread out across the craton. And a big chunk of those greenstone belts consists of Neo-Archean volcanic and sedimentary sequences. As you can see here, the CAM group is the mafic-dominated volcanic, and then you get into the Banting group, which has more felsic volcanics hosted in it, and then the Duncan Lake group is a big portion of mudstone grave-archy sequences. The Slave Craton is kind of unique because the extent of the basement, so there's in the western part here and the central western part, there's basement under the greenstone belt, but when you go to the central part here, approximately this line here, there's no more basement underneath the greenstone belt, so the whole eastern part of the Slave Craton is considered very juvenile volcanic sequences, those greenstone belt here, and that's including the Hope Bay belt up here. You can see a total of approximately 20 million ounces of gold has been produced from the Slave Craton so far. So not as, you'd say, not as prolific in terms of gold compared to the Abitibi, the Superior Craton and Abitibi. And I just, for those not familiar with Slave Craton and the size of it, it's actually a tiny craton. So this is outlining the Abitibi right here, just to show you the size comparisons here. So if we go into the Hope Bay area up here in the Bathurst Block, it's situated here. The greenstone belt is approximately 80 kilometers long and 30 kilometers wide, greenstone belt. It's completely surrounded by granitoids on each of the flanks. There's been a lot of work done on the volcanic stratigraphy of the belt. So it consists of 5 panels of volcanic rocks spanning approximately 50 million years of time. 2716 to 2662 is the time frame of the Hope Bay greenstone belt. Note there's 2 H's here I show up here. They've been done by that's the emplacement H's of the granitoids. So these have been done in the 90s, I think. So we actually thought that there's space in the stratigraphy to do a little more of these emplacement of the granitoid intrusions here, the timing of them, because nothing has been done on age dating these granitoids right here. So that's part of this project. Is we've been collecting, doing some field work up on the edges of the greenstone belt to collect some of these beautiful granitoids here, and that will help us constrain the relation between granitoids and the volcanic sequences in the Hope Bay belt. So we found that was a good time to do that when we were up there. So the whole eastern flank here is granite monzonite rocks. It just shows some samples of the granitoids here. And we have more tonalitic variety of granitoids on the eastern flank here. And we have some granite gneiss component right here, down here in the southeast part of the area. So the western flank granitoids, took 2 samples here. They all come in 2610 million years old. So they are in line with the previous date up here, taking all the way up here. So all the western flank here is quite younger than the greenstone belt. On the eastern flank, it's a little more complex area, but we've been dating some of these tonalites right here, and there's two samples that gives 2681 AIDS, and 2 others that's approximately 2686 million year old. So there's sin with the volcanic belts, the greenstone belt. I will comment on that a little later. So just a little bonus sample. We've been collecting a granitoid that's actually within the belt and in Chenolith in a mafic dike. And we have a pretty good 2708 million year old constraint on this. So that gives us a little bit of a hint on what might be underneath the Hope Bay belts in terms of basement, if you will. So that's still sin with the old packets of volcanic rock in the belt, the Flake Lake volcanic. Yeah, so just to sum up some of our geochronology studies that Mike has done, all of these samples here. So we have a eastern flank that's 2610, so younger than the belt, and we have a sin volcanic intrusions right here. That's part of some of the sin volcanic intrusion is sin with the Windy Lake felsic volcanics right here. You can see they've been really well mapped out in terms of the age here, and they fit with the 2686 million year old part of this granitoid right here. Oh, yeah, tonalite. We do have a younger component here, down here. We have an age on 2649, so younger than the belt, but it's a little bit complex granitoid here. I won't comment on this in this talk. It's a high metamorphic rock, so it's a little difficult story to solve. So if we have this in mind, these 8 emplacement ages of the granitoids, if you have that in mind, and we go now to the crustal connectivity of the Hope Bay, this is going to be important. So we've been carrying out a huge MT grid over the Hope Bay belt and the Bathurst Block. As you can see here, these are all stations, MT stations. Carried out in the summer of 24, I think, or 23. So if we look at some of the results of the crustal connectivity, here I show some horizontal depth profiles. We have 4 depth profiles. The first one is for 4 to 5 kilometers depth. The next is 9 to 11 kilometers, 13 to 16 kilometers. And then the deepest one I have here is up to 27 kilometers depth, 23 to 27 kilometers. So pay attention to these 3 conductive anomalies that's seen throughout the belt here. You can kind of sense the belt's outline right here. So that's C1, C2, and C3. These are situated in the belt. And then if we go down to 9 to 10 kilometers, we are losing the C3 anomaly here just up south of the Madrid deposits. Right here, it's gone now, but these two, C1 and C2, is still evident here. So this is called the Spider Lake anomalies because they're actually just north of the Boston deposit. They don't come up at the Boston deposit, but 5 kilometers to 10 kilometers north of the Boston deposit. So if we go further in depth, these anomalies is still there, and they connect to this deeper C4 anomaly, I call it, right here. It's a huge elongated anomaly that crosses the belt in a northeast southwest direction right here. And that's important that these two anomalies connect into this. I'm going to show you a vertical slide in a minute. Also pay attention to all the resistive crust that's there throughout the depth. I call these the R1 and R2 resistive part of the crust under the belt. And that's also an interesting observation. So if we cut the belt right here from south to north, this is how the slice looks like. So we have those two C1 and C2 anomalies, spider leg anomalies. You can see they connect with this bigger C4 anomaly here in the central part, or just south of the central part of the belt. And you can also see the Madrid anomaly right here, the Madrid deposit. I call it the C3 anomaly, but the reason why that stopped at depth was, you can see it right here, it's a hockey-shaped feature. And it's not connected to anything in a deeper part of the crust in terms of conductive patterns. So this MT profile is relatively interesting, especially these R1 and R2 resistive zones that goes all the way down to 40 kilometers depth. It's not something that I'm familiar with. We have seen in the Abitibi, some of the Abitibi MT sections. Here I just stole one of my own MT slices from Matheson, but this is pretty familiar profile of at least the Abitibi crust, that you have this mid to lower crustal high conductive zone. And then you have a 10 kilometers more resistive part of the crust. But we don't see that in the Hope Bay greenstone belt. So it's a little different crustal architecture, I think. If we go up and slice some east-west slices right here, close to the Madrid deposit, just so we can see the Madrid deposit from south to north here. It's pinching out with depth here, and it's just a small area that you see here. It's still conductive, but it doesn't connect with the C4 anomaly in depth here. So this C4 anomaly is really interesting, and it's been I've been really thinking a lot about how to interpret this as it crosses the whole belt right here. And you can, if we slice it from northeast to southwest, then it looks like this one. So you can see you have a part of the finger that comes up to the Hope Bay north of Boston is still evident here in this northeast southwest slide. So to sum up this C4 anomaly right here, which is the most interesting, is we've done just a very cartoonish sketch here showing the C4 anomaly. So how it fits in with the all the emplacement ages that we've been doing in this work. We have the eastern flank of granitoids, that is syn with the syn volcanic, granodiorite, diorite. It's syn with the volcanic belt. And then we have the later 2610 granitoids. And the take-home message is that this C4 anomaly kind of crosses under the whole packets of granitoids, even the 2610 million-year-old rock. So one conclusion could be that the C4 anomaly is actually a later event, at least later than the 2610 million-year-old granitoids on the western flank of the belt. So I started looking at the orientation of this and put it into a bigger context, regional context. The Hope Bay is actually relatively close to the Thelon tectonic front. That's right here on the craton margin. The whole Bathurst Block is actually part of, should be considered a craton margin. And there's a lot of tectonic activities that's been taking place along this boundary right here. And the C4 anomaly has exactly the same orientation parallel to the Thelon tectonic front. So here's just a view that's a little bigger in perspective. Hope Bay is situated right here. And the Thelon tectonic front is a huge tectonic front that goes all the way up here and all the way down south, further southwest. And there's been at least two paleoproterozoic events. The Arrowsmith orogeny, where the slaves abducted under the Queen Maud Block. So a lot of the Queen Maud Block granolite facies rocks was created during this Arrowsmith orogeny. That's at least the story. The Thelon orogeny was later on, 2.01 to 1.91. That tectonic style is still debated a little bit. It's a collisional orogeny or it's an intercontinental orogeny. It's a little bit debated still, but it must have had some influence in the deeper part of the craton margin, I think. So could this feature be related to a stress field that was started at the tectonic front? So could it be a structural feature that has some alteration product in it that's conductive? We kind of discussed that in the manuscript, so that's one way of explaining this C4 anomaly. So that's so these conductive fingers that goes up to surface here. Just gonna go back. Oops. So these conductive finger that goes up in the Spider Lake area, are they a paleoproterozoic origin, or are they paleoproterozoic origin that's been using already existing Archean structures to surface? We don't know that, but those are the discussion that we've had in this manuscript. So that's how you at least try to combine geochronality age states with an MT study. So yeah, that's all I have for you today.